packet, an NMSI acid-base packet. We're on exercise 6. I'm breaking this up into some small videos only because of technical issues. But I'll try to keep the videos, any video, to an hour or less, and then post it. Okay, so we're on exercise 6. This is on page 9. I'm going to do this on line paper just because I want a little bit of space and don't want things to seem so crowded. Sometimes the boxes that they give you are really not, to me, enough space. So I'm going to take this one here. So looks like that. Remember that we made a correction over here under pKa, that should be negative log Ka, where I'm circling the cursor. I'm assuming you can see that on the video. So what we have is, again, to go over this, it's really the 4 major variables that you have with acids and the 4 major variables you have with bases. The hydronium concentration is on the far left, H+, and then the down below the arrows show you how you get from H+ to pH and from pH back to H+. So you just follow those steps to get between those two. To get an equilibrium constant for an acid, which is known as the acid dissociation constant, you use a combination of an ice table and the Ka, the Ka formula, basically the law of mass action for the acid. Once you have that, if you need a pKa, and we'll be talking about that later and what that would be used for, you can use the arrow there. It says negative log of concentration of Ka. And it really should just be Ka. So I'm going to correct that. You can make this correction too. It's not a concentration of Ka. So I'm going to change that. I'm going to change it for Kb as well. So do a little on-the-spot corrections here. And there we go. Okay, so negative log Ka. Similarly, over on the base side, you have hydroxide concentration, OH minus. You can see how you get back and forth between that and the POH. All a P means is negative log of something. And the reason we use pHs and POH is they give us a nice scale between 0 and 14 instead of these messy looking 10 to the negative 4s and those types of things with those exponents with negatives. So it just gives us a nice user-friendly scale. Kb you calculate the same way, except you're using a base dissociation equation down there at the bottom along with an ice table. And then down below the center arrow, Kw is kind of in the middle of it all. That's water. Water is a neutral substance. It's right in between acids and bases. And if you go straight down that downward pointing arrow, those are the formulas that connect the two sides, that connect the acids and the bases. So that's how you would do some sort of a translation between acids and bases. Over on the left, you have the 6 strong acids. Over on the right, I have not completed that list of strong bases. I will do that. And Henderson-Hasselbalch down at the bottom is something we don't need for a few more days, so you can ignore that. Okay, so let's go ahead and do this. So the question is asking us... So the question is asking us for 1.10 to the minus 5 molar OH, so that's hydroxide, calculate the H+, the OH, you already have that, the pH and the POH. All right, so there's several different paths you can do this, but let's go ahead and do it directly from the concentration of OH to the concentration of H+. And if we go to our... And by the way, it does say in the problem, which I didn't copy this down, that's at 25 degrees. That's crucial because everything we're saying here applies only at 25 degrees. And they'll almost never give you a problem that's not that. So it's at 25 degrees centigrade. If they do, they're just testing to see if you understand what would you do if the temperature was different, but they won't ask you to do any real heavy calculations with that. Okay, so here we go. So we're 25 degrees. So we're going to go to our roadmap here, and we see that there is a relationship that connects H+ and OH. It's right here. It's the second formula down in the middle, and it says Kw equals H+ concentration times OH minus concentration, and that equals 10 to the negative 14. So we can go ahead and plug in those numbers and do that. So we're going to write H+ concentration, which is what we're trying to find. H plus concentration, which is what we're trying to find, times the OH minus. I'm going to omit the 1. It's not really necessary. I'm just going to put 10 to the negative 5th. Oftentimes, more often than not, there will be a coefficient there other than 1, but this doesn't have it, so let's just leave it off. And that's going to equal 10 to the negative 14th. Okay, so, and again, once you get into a math equation, you should be using parentheses on the calculator. So I'm going to go ahead and divide both sides by 10 to the negative 5th. Okay, and this cancels out. And so what we have here, you got to be, kind of adept at your exponents. It's negative 14 minus negative 5. So it's going to be 10 raised to the negative 14 minus negative 5. Double negative there, which becomes negative 14 plus 5. So the answer there is going to be 10 to the minus 9. Okay, and so that is the H plus concentration. All right, now let's figure out the pH and POH. And as you get good at this, you'll realize that if the OH concentration is 10 to the negative 5, the pH is 5. But let's go ahead and write it out properly. So POH, write out the formula every time so that they become natural and you have them memorized just naturally. Have them memorized. So that's going to equal, P is always, the letter P means negative log of, and then you put 10 to the negative 5 in there. Okay, so practice your calculator skills. I'm going to do this one right here. So you hit the negative sign down at the bottom here. Hit the negative down there. Let me clear that. Negative log up here. And then it's 10 caret negative again 5. 10 to the minus 5. Close the parenthesis. Don't forget to do that. And you hit equal. And you get 5. And soon enough you're going to just learn that right away that's 5 without having to punch it in a calculator. So the POH is 5. Alright, now we can calculate the pH several ways. Let's go ahead and do it the way we just did POH. So pH equals negative log of the H plus concentration, which we calculated was 10 to the minus 9. And as you can see from this example, that's going to be 9. Okay, the other way we could have done it was if we knew POH first, okay, then you use the formula pH. Let me show you on the road map. You use this very first formula up here in the middle. pH plus POH equals 14. So pH plus POH equals 14. So assuming we knew POH first, then it would be pH plus 5 equals 14, and pH equals 9. Okay, so we generally judge basicity and acidity, or alkalinity, which means how basic, and acidity by pHs. So a pH greater than 7 is going to be basic. So this is a basic solution. It's on the high side of the number 7, and that makes it a relatively weak base. Get up into 12, 13, 14, it's a strong base. All right, so let's move on to B. We'll do that one a little bit faster. All right, next problem, B on exercise 6 is 1 times 10 to the minus 7th molar of OH concentration. So we want to figure out the H plus concentration. Let's do it a little differently this time. Again, just taking a different route to the same ends. We're still trying to figure out H plus concentration, pH, and POH. So let's first figure out POH this time. So we're going to go directly to this. Okay, and that's going to be negative log of 10 to the minus 7. So again, do that on the calculator, practice your calculator skills. Okay, so we have negative sign down here at the bottom. Sign here, negative sign, log, and it's 10, caret, the negative sign again at the bottom, 7, close parenthesis. Be sure that's the way you have it punched in, and that's going to give you 7, of course, okay? Alright, so we got that. So now we're going to take a different route than we did for part A. We're going to say, it's the same steps, it's just doing them in a different order. pH plus POH equals 14. Again, that's right on your roadmap in the center on the bottom. Okay, so we know that this POH is 7. pH plus POH, so therefore pH equals 7. I think you can tell intuitively that this is a neutral substance because they both are 7. pH and POH. Alright, let's go ahead and figure out the H concentration though. So what's the H concentration if you know the pH? So we come back to the roadmap and we want to get the H plus concentration starting with POH. So we use this arrow down here, and so you raise 10 to the negative whatever value of pH you have, and the value of pH we have is 7. So let's go back. So the H plus concentration is 10 to the negative 7. And we don't need to do anything more with that. So our OH concentration was 10 to the negative 7. Our H plus concentration is 10 to the negative 7. That's a neutral substance, and that's called water. So this is neutral. All right. Let's move on to C. And now they have 10 molar H+. And a lot of students find this trickier than the ones with the 10 to raise to some negative exponent. This throws some students off, so let's go ahead and do this. So this is 10 H+. Okay, so we want to find, that's the concentration of H+. So let's go ahead and find the pH of that. So pH equals negative log of 10. Just that simple. So let's go ahead and do that. Over here, negative log number 10, close parenthesis, and it gives you a negative 1. Okay. That's kind of weird. Okay. So let's see what the POH would be. So we know that pH plus POH equals 14, and we got pH at negative 1. Therefore, POH must equal 15. All right. So what would be the concentration? That's really what they're asking us for here. Doesn't that violate some kind of rule to have a pH of negative 1? Well, it it's basically the way the numbers work out. And so this is actually the correct answer. You have a pOH of 15. So you have a pH less than what we would normally say our minimum is of 0, and a pOH greater than the maximum of 14. So let's go ahead and figure this out, because what this is really telling us is the hydroxide concentration. So what you're going to do is say, to get the hydroxide concentration, the OH minus, that equals 10 to the negative pOH, and there it is. So you can do that. I mean, that's your concentration of hydroxide. It's just a very, 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 very small number. And that's the answer to that. Okay, so that takes care of those. So a lot of these are just simply learning to read the roadmap, just kind of navigating around it and getting from one variable to the next. Okay, it's very mechanical at first, but then eventually it starts to become more intuitive. You understand the reasoning behind why you're doing these calculations. Okay, now we're going to continue on with exercise 7. And this is going to be kind of easy because you just did it on the previous problem. It didn't ask you to, but I asked you to figure out the pH and the pOH. So what I want you to do is also figure out the OH concentration and the H concentration. Just figure out all 4 of them. Just keep practicing this, and it becomes very natural, and you start to see the connections. All right, so it's giving us 1. I'm going to go ahead and write this on the sheet. 1 times 10 to the minus 3 molar of OH. So let's figure out pOH. So go to your roadmap. If this isn't memorized already, and it's okay if it isn't, and you have an OH concentration in the upper right hand corner, you need to move over to pOH. So down here it tells you that that's going to be the negative log of the OH concentration. So we're simply going to write negative log of the OH concentration. Negative log, and I'm going to omit the 1, 10 to the minus 3. And do you have this one memorized yet? It's going to equal 3. All right. If we know that the pOH is 3, we have another formula. pH plus pOH, it's on your roadmap, equals 14. So that means this is going to be pH plus 3 equals 14. So pH equals 11. Okay, so is that a basic solution or an acidic solution? pH greater than 7 is basic. Pretty strong basic. Okay, let's go ahead and figure out the concentration. So for the concentration of OH we already have. So let's figure out, I'll just move right here, the concentration of the hydronium, the H plus or H3O plus, is going to equal, don't need to memorize these, you got a sheet. It's going to come over here. So you've got a pH and you want to get to the hydronium concentration, so it's 10 to the minus pH. Okay, so that's 10 to the minus 11. Okay, and there we go with that. So you can see there's a lot more hydroxide ions than hydronium ions. So this is a basic solution. 10 to the minus 3 is much larger than 10 to the minus 11. Okay, let's do the next one. This is 1 molar. So we're going to just do it the same way. So it's 1 molar H plus. So if we want to know the pH, okay. And if you don't know that one, you go to your calculator. And we have negative log of 1. Close a parenthesis. That gives you 0. Okay. Therefore, we know we have another formula that pH plus POH and we just figured out the pH. Okay, and there you go. And if we want to know the OH concentration, which equals 10 to the minus 14. So very easy to get around with these once you practiced it a few times. Okay, that's it. So let's move on to number 8. Okay, so the pH of human blood was measured to be 7.41 at 25 degrees centigrade. That means all of our formulas apply. Calculate the other three things: POH, H plus, and OH for the sample. Okay, so we're given a pH, so let's go first for POH. That's pretty easy. That's an arithmetic problem. So pH plus POH is 14. We're told that this is 7.41 plus POH. And so that's going to give us just simply 14 minus 7.41. And that gives us 6.59. Okay, so there's the POH. We go ahead now, we can figure out, come over here and figure out the H plus concentration. And the formula for that is equals 10 to the minus pH, which equals 10 to the negative 7.41. So that's not one you can do in your head, so go ahead and punch that in. So it's 10 negative, whoops, not negative, 10 caret negative 7.41, and hit enter on that. And now what you get here is 0.0, you get 0.00000039. Okay, in scientific notation is 1, 2, 3, 4, 5, 6, 7, 8. You want the decimal in between the 3 and the 9. So it's 3.9 times 10 to however many decimals you had. And you just use some common sense. Was it a really small number there or a really large number? It was really small, so it becomes negative 8. All right, so there's that. And then the, that's it, right? So we have everything else. Right, POH, pH, yeah. Okay. All right. Oh, we didn't figure out OH. That's right, we didn't. Okay, so let's do that. So there it is, OH minus equals 10 to the minus POH. And that's 6.59. Again, just go ahead and use the calculator there. And that gives us 0.000000257. So we move the decimal over. We need to get between the 2 and the 5. Remember, we want a number between 1 and 10 here. So 1, 2, 3, 4, 5, 6, 7. So 2.57 times 10 to the minus 7. Oops. Okay, they put 2.6. That's fine. That's significant figures. And that's it. Okay, next one. These are easier than the first few exercises in this packet. Okay. Strong acids. All right, so here we go. pH of 0.1 molar nitric acid. So, same thing, doesn't change. Let's see, I'll do nitric acid over here. And I'll do hydrochloric acid down below. Okay, so 0.1 molar. They want the pH, so pH equals negative log of the hydronium concentration. So let's go ahead and write the equation for this. It's H2O, and I use the expanded formula with the H2O in it. I just like it better. I like to see what's reacting with what clearly. Plus HNO3. And a strong acid means that every single one of these hydrogens on every single one of these nitric acid molecules is going to come off and come over and jump to the water. So that's going to leave you with an NO3, because that hydrogen went away, but not the whole hydrogen, not the proton and the electron, just the proton. So that makes this an anion. And then it jumped over that proton to the H2O. So that's considered to be an H3O now, but it's not a total hydrogen atom that came over. It's just the proton, so that gives it a positive charge. Okay, so this totally dissociated. So what they want to know is the concentration of this. And if there was 0.1 molar of HNO3, then there's going to be 0.1 molar of this after the reaction takes place and 0.1 molar of this. Okay, so everything's 0.1. So stoichiometry in strong acids is very easy, because whatever molarity you have here, however many moles you have here, you're going to have the same number of moles there, same number of moles there. It totally breaks apart. Okay, and so that's going to be and it was 0.1. Could have put 0.1, that's okay. We'll just live with that. So negative log 0.1, and that gives you 1. All right. So pH is 1. So pH plus POH equals 14. They're not asking you for this, but we're going to do it anyway because we want to get good at this. That means the POH is equal to 13. Okay? All right, anyway. Now they're asking you for the pH of 1 times 10 to the minus 10 molar HCl. All right, so this is a strong acid, but what you're going to see is it ends up with a basic pH. So let's go ahead and do that. So pH equals negative log of H plus, which equals negative log of the number they give us, 10 to the minus 10. We don't need the 1 there. And that equals negative log 10 caret negative 10 close parenthesis. And that gives us 10. So that's a pH of 10, means that's basic. It's not acidic, it's basic. Very, very small HCl concentration there. Okay. All right. Okay, so now they want to calculate the pH of 5.0 times 10 to the negative 2 molar NaOH. NaOH is one of the strong bases. That means it's going to totally dissociate. So if we wrote an equation for that, it would look like this. And you'll learn the strong bases and acids very shortly. You'll have them all memorized. This is the reaction you did when we did calorimetry that let off the heat that was the exothermic and you saw the temperature go up. We put sodium hydroxide in water. That's exactly what we did. Okay. So what's going to happen here? The sodium is going to break off into a cation. It's a spectator. It doesn't do anything further. Then what happens is the OH breaks off. Minus. Okay. And then we're still left with water on this side as well, as long as we write water into the equation like that. This is a base. That means it's going to attract a proton. Now think about it. If it attracted a proton from water over to there after it dissolved, then that would become water. It would become H2O, and that would become hydroxide, OH. So it really doesn't do that. You just say it just dissolves it, and the water remains as water. Like that. It doesn't turn into H3O plus like it did with an acid. It just stays like that. So anyway, that's kind of a sidebar here, but let's go ahead and do this. So the pH of this, so pH equals negative log of H plus concentration. But we don't have the H plus concentration. We have the OH minus concentration over here. Okay, so we're going to have to figure out POH first. So POH equals negative log. Again, this is all on your roadmap. Go over there and check it out and find these formulas. Which equals negative log of 5, can't ignore the coefficient this time, times 10 to the negative 2. So let's figure out what that's going to be. So we have negative log, brings us a parenthesis, 5 times 10, caret, negative 2, close parenthesis, and equals, and it's 1.3. So POH equals 1.3. So to find pH, we use our formula pH plus POH. Didn't say 25 degrees here. If it doesn't say it, you assume it. Or if you're on the AP exam, you write that you're carrying that's your assumption. We're assuming temperature at 25 degrees. State your assumption. Okay, equals 14. So that's going to be 1.3 plus pH equals 14. Therefore, pH 14 minus 1.3 equals 12.7. All right, and that's that. Okay, so that takes care of this first set of problems. I'd like you to get the second set done over the weekend. The second set is due on Wednesday rather. This set is due on Tuesday. And if you haven't gotten it in already, and that's it. I'm gonna move on to the second set today and have those solutions up later today.